My name is Hubertus Thomas. I'm chairing the session on the research on complex plasmas and dusty plasmas, and especially the PK4 program. PK4 is a joint Russian-European project started 10 years ago. So exactly in November 2014, we had the assembly of PK4 in the Columbus laboratory. So this is not only giving an overview of PK4, but also a kind of celebration. And this will be continued. The main talk of PK4, the overview talk, is in a later session. We will start here with more detailed presentations from the PK4 community, and also we will look into the future with the last talk of this session. I want to also remind you that this is, as I mentioned, a European-Russian project. Unfortunately, all our Russian colleagues are not able to attend this workshop, but their contribution is really elementary for the whole PK4 project. So I want to mention that, and I hope that more colleagues, or those colleagues, especially Andre, Sasha, and Andre, are online available, and they can follow the presentation. So the first presentation is by Ishita Yoshi. She did her PhD last year, partly on PK4 data analysis and simulations for PK4, and she will give you an overview on emergence of collective effects in complex plasma. Ishita.
Hello. Oh. Thank you. So yeah, I'm going to be talking about the work that I did during my PhD. There's the QR code if anyone's interested. Oh no. Oh. So I'll briefly talk about the scientific objectives, and the work that I'm talking about today was done using molecular dynamic simulations, so of the experiments on board the PK4. And I basically want to be talking about two topics. So firstly, collective effects in conventional fluids, so stuff like turbulence, and collective effects in electrorheological fluids, so string formation. And both of these will be using complex plasmas as a model system. And so this was a numerical study of collective behavior in complex plasmas, and the main question was, how do these collective effects emerge from interparticle interactions? What parameters do they depend on? How do we control their onset? And the molecular dynamic simulations were done using a program called LAMMPS. And we only simulated the particle dynamics. And these were all three-dimensional simulations with periodic boundary conditions. We used a Yukawa interparticle potential. So that's the same thing as a Coulomb potential, but with an exponential decay term. There's a Langevin dynamics thermostat to the simulation, so there's a background gas, there's friction from the background gas that introduces damping in the system. We have Brownian motion of the background gases at a specified temperature and pressure. So the first topic I want to talk about is turbulence. The term was coined by Leonardo da Vinci in the 15th century, and despite being one of the oldest investigated problems in physics, a complete description and the ability to predict its onset is missing to this day. And the main problem with turbulence is that it's really hard to define. What we have are signatures and hallmarks of things that we associate with turbulence. We don't have a definition. So what we did here in this work, and the QR code for the paper is up on the screen, what we did for this work is we basically came up with a checklist, and we said that if we have the things in the checklist, then we have turbulence. So turbulence needs to have vortices. It needs to have disordered and irregular flow, so rapid changes to flow profile, so velocity vectors, pressure, density, etc. You need to have an increased rate of mixing. If you compare that with laminar flow, where you have these parallel sheets with very little mixing between the layers, in turbulence you have these vortices that mix things up between the layers quite a lot. You have increased flow resistance compared to laminar flow, because turbulence creates drag. And you have the turbulent power spectra, as described by Kolmogorov, with a -5/3 power law in both space and time, as energy, you have energy cascades through the scales. And that's the checklist for turbulence in undamped systems, so conventional fluids like water and air. But if you have damping in the system, like we do for complex plasmas, then you also need to check that your vortices are able to cascade the energy through the scales before they die out from damping. So you need to make sure that your cascade rate is higher than your damping rate. And we're also looking for intermittency, which is something you see in fully developed turbulence with rapid changes, fluctuations to flow parameters. So these are the molecular dynamic simulations. You have a 3D simulation with more than 24,000 particles and periodic boundaries in all directions. This is a 2D slice of number density that is cut from middle of the simulation box. And you see there is this circular cavity in the middle. So what we have is an obstacle in the middle of the box, and this was simulated by just putting a point charge with 4 orders of magnitude higher negative charge than the particles, so that the particles repel it. And that acts as our spherical obstacle, basically. And when you give the particles speed in the positive x direction, so they all move from the left to the right, you basically see, okay, they're flowing past an obstacle, does the flow become turbulent? So that's the gist of the simulations. And as you see in this plot, so the top plot is a number density plot, and the bottom plot is a vorticity plot averaged over 1 second. The particles are moving from the left to the right. So on the left side of the plot, so near like x = 0, you've got basically laminar flow here of particles flowing towards the obstacle. They're flowing in parallel sheets. There is no vorticity. And as they flow towards the obstacle, you notice 2 things in the number density plot. Firstly, there's a bow shock in front of the particle, in front of the obstacle, so in the 4 wake. There's a bow shock here. And then there are mark cones behind the obstacle, so in the wake region. And in the vorticity plot, in the same regions where you have these shock waves or shock fronts, you've got increased regions of increased vorticity. And what we'll find out is that actually in damped systems, so here pressure is 10 pascals. So in systems with damping, you need these shock fronts to produce turbulence, because you have a flow of particles directly into a shock front, and that region of increased interparticle interactions is what leads to turbulence in a damped system. So now we are looking at disordered and irregular flow. So this is a plot of the velocity perpendicular to the direction of motion of particles, so in the y-axis over time. So we've compared the vertical velocity in 2 regions. So one is the laminar region, so away from the obstacle, and you can see that there the perpendicular velocity is basically 0. And if you look at the region just before the bow shock, you see that the vertical velocity does change over time, and it's -10 millimeters per second, which is quite a big change here. And it does change rapidly over time. So you have this is also an example of intermittency, where you have rapid changes to the flow parameters. The flow is chaotic in the region just before the bow shock, but also you have increased fluid mixing, because now you have velocity in the direction perpendicular to the motion, so you don't have these parallel sheets of motion. You've got increased mixing between the layers. Increased fluid resistance. So that is a heat map of the kinetic energy. So the plot is cropped to show just the region near the bow shock. So this kinetic energy is normalized by the kinetic energy of the laminar region. And what you notice is a drop in kinetic energy in the region where we saw increased vorticity. And so the driving force that is driving the particles, giving the particles that velocity in the positive x direction, is applied equally throughout the simulation box. But you see a drop in kinetic energy in the region where we have vortices, and that signals an increased flow resistance. Now, looking at the power spectra, here are the power spectra in time and space, and you see that they have a -5/3 power law, and also you have, we are in the regime where the cascade rate is higher than the damping rate, so we're in the regime where physically we're able to get turbulence. So we also have a turbulent power spectra. So why do we think we have turbulence in our simulations? Well, we tick all the checkboxes. So we think we have turbulence in the simulations. Okay, now let's look at the onset of turbulence. So here is a plot where I have taken the gradient of the power spectra slope. I've normalized it by minus 5/3, which means the value here of 1 means you have a power spectra slope of minus 5/3. And we're changing two parameters here. We're changing either the particle charge, so that's the 3 different curves here, or we're changing the flow speed that you give to the particles as they flow past the obstacle. And what we see here is that by changing if you keep one of the parameters constant, by changing the other parameter, you can get turbulence in the simulations. And that's because both of these parameters, the flow speed and the particle charge, affect the Mach number or the Reynolds number. So if you keep one constant and change the other, you reach turbulence. And here we also see intermittency. If you look at the simulations where you don't have fully developed turbulence, but you're developing turbulence, you have these intermittent puffs of vorticity. So in the same region, but changing over time, you've got these puffs of vorticity. And what these are basically is 1 or 2 particles going out and moving in a loop and moving sort of in like starting vortices one by one. And here you can really see turbulence at a particle result level because you see individual particles go out and form these vortices before you have fully developed turbulence. And this also is similar to the same pathway that you have turbulence develop in conventional fluids. We also did the same analysis for a very low pressure simulation to make sure that we also see turbulence in a system without damping. And in this case, we did observe subsonic turbulence, so when we didn't have any shock fronts. And so we didn't need shock fronts in a system without damping to get turbulence, and that shows that, well, the shock fronts are needed in a system with damping to really push the cascade rate higher than the damping rate. So for this project, we reliably triggered the onset of turbulence by changing one of 2 parameters, either the particle charge or the flow speed. And that's because both of these parameters affect Mach number and Reynolds number. And we noticed that shock fronts were important for the development of turbulence in damped systems, and they weren't needed in undamped simulations. So the next topic that I wanted to talk about was collective effects in electrorheological fluids. So you have formation of strings. So this is an example of electrorheology where you apply an electric field and the particles align themselves in long chain-like structures. And we basically want to understand why these strings form. And in conventional electrorheological fluids, that happens because of interparticle interaction, because the particles themselves get polarized, you have a positive and negative end, and then they attract each other, and then they form these long chains. What happens in complex plasma as well, you have a negatively charged particle, and you have a lot of ions basically around the particle. And when you apply an electric field, that causes the ions to get focused directly behind the negatively charged particle. So the particle itself doesn't get polarized, but it acts as though it is just because of this positive ion wake behind the particle. And what we found actually is that this doesn't need to be effective interparticle attraction to form strings, like in conventional electrorheological fluids. Just reducing the repulsion between particles along the direction of the electric field is sufficient to form strings. And this was an experiment that was done on the PK4. So we used argon gas, 11 pascals of pressure, and we formed stable strings. We turned the plasma off for a fraction of a second, and that destroyed all the stringy structure that we have in the experiments. And then we turned the plasma back on and slowly allowed the structure to form again. And we basically tried to simulate that. And the way we did this, we had an electric field. So the effect of the electric field that's changing direction constantly, we simulated that by basically putting, instead of a wake just behind the particle in one direction, we put 2 wakes on either side of the particle. So the interparticle potential is basically the Yukawa potential and the potential due to the wake on either side. And this is what the interparticle potential looked like in the simulations. The black dashed line is the Yukawa interparticle potential, and the red solid line is the combined potential, the modified potential. And you can see that the modified potential is still repulsive. It's not below zero there. It's still repulsive long range, but the repulsion is reduced compared to the Yukawa potential. So we still used a repulsive at long range interparticle potential, and we reproduced the entire experiment without using long range attraction. So that's our main result from this work. And I hope the animation works. No? That looks like it doesn't work. Sorry. This was supposed to be an animation of the, or a video of the simulation where you have these long chains of particles, you turn the plasma off for 0.3 seconds, and all of this stringy structure basically gets destroyed. You have no structure, and then you wait over a couple of seconds as the structure reforms again. So sorry that this is broken. Again, this is a 2D slice of a 3D simulation. Oh no, what did I do? No, I pressed something. Thank you, sorry. Yeah, I'm not sure if that's working. Yeah, well, but so then we plotted the pair correlation function to look at the structure of the particles. And this is a crystalline pair correlation function, and you can see that the initial big peak is split into a primary peak at the interstring distance and a secondary peak at the interparticle distance in the string. And that's before we turn the plasma off. Then we turn the plasma off, and initially it looks like liquid, the red dashed line. And then given enough time, it starts to look more like a gas, the black solid line. And then now you know all the structure is destroyed, and you turn the plasma on again, and it takes like 3 or 4 seconds to go back to looking like the original crystalline distribution with the peak splitting there. Now, we also did this in 3D, so looking at the 3D pair correlation function. And to make it easier to plot, we took their integrals in theta and phi. So plotting g theta and g phi, that's for the simulation. And that's for the experiment on the left. And on the right, that's for the simulation. And the main important takeaway from these plots is that they look qualitatively very similar. The shape of the plot is very similar. The peaks are at the positions that they should be. And what we're seeing here is that we're able to qualitatively reproduce the experiment very well by just using an interparticle potential that is slightly less repulsive rather than using an attractive interparticle potential. We also plotted, so stringiness, this is the average neighbors, nearest neighbors a particle has. If it's in the middle, it's got 2 neighbors in a string, 1 on either side. If it's on the end, it's got 1 neighbor. And we use this sort of as an order parameter. And you can also see here we compared the experimental and the simulated results, and they're qualitatively very similar. So we were able to reproduce the experiment in the simulations very well with very good qualitative agreement just by using an interparticle potential that's slightly less repulsive, and that shows that long-range attraction is not necessary for string formation. Reducing the repulsion seems to be enough. And yeah, that's my talk. Thank you for listening. If there are any questions, I'd be happy to answer them.
Thank you, Ishita. Very nice. Are there questions in the audience? Peter.
Hi, thanks for the nice talk. For first part, I have a question. I mean, you mentioned that your obstacle is just a point charge, fixed, and it certainly has some kind of interaction with the particles, which is kind of soft. And I was wondering if one can tune this so to say, the hardness of the obstacle. It could be a hard wall, or it could be some magnetic, which has a softer potential. So if that would influence the onset of turbulence, especially on the bow shock part.
Yeah, I can imagine. You can definitely tune the interaction between the obstacle and the particles in the simulations. So the reason I chose a point charge, firstly, is because I wanted to use a charged sphere initially, but it's easier to simulate a point charge and they act the same way. But also in experiments, we see when we put like a big ball or an object that's much larger than the particles, you have a cavity around it anyway. And so that is still quite a soft interaction, which is why I used this, because it was similar to what we see in the experiments if you put a much larger ball.
And was that Coulomb or Yukawa interaction between?
It was Yukawa still. But yeah, I guess you can do that. I have not done the simulations by using a different type of interaction between the particles. I'm not sure how that would change it, but I chose it because it was what we see in the experiments.
Okay. And to the second part, I mean, you mentioned that you modified the interaction potential with because of this electrolytic effect, but that was an anisotropic, I guess. So you modified only in one direction. Yeah, on the perpendicular, it was still pure Yukawa, or
yeah.
How?
So on the perpendicular to the electric field, it was still pure Yukawa, and only in the direction of the electric field
and you
was
had some
it.
smooth transition depending on the angle, or how was that treated?
So the simulation does have the capability to change the angle, but in this case, we only chose one angle, basically depending on the angle of the electric field. So we had the same angle, but it does have the capabilities that you can change that.
Mm-hmm. Okay, thanks.
Thank you.
Ishita, thank you for the talk. Can you tell us how cascade rate and vorticity is defined or are defined?
Oh dear. So I mean, vorticity. We basically took the. So we made bins in the simulation, and we looked at vorticity by. So you can see the bins there, and the vorticity was basically looking at the difference in Vx and Vy in the neighboring bins and the top and bottom bins to the bin that you're interested in calculating vorticity, and cascade rate was. I can't remember the formula for that off the top of my head. It's been a year.
Just qualitatively.
Qualitatively, the cascade rate was dependent on. Oh boy, I can't remember that off the top of my head at the moment. You calculate the viscosity of the. I'm sorry, I'm blanking on that right now.
Thank you.
Do we have more questions? There's also a question and answer session afterwards. I kept this a bit longer because I like it, the questions and comments directly to the talk. I have one question. You were presenting the first part on the collective effect with the flowing dusty plasma. PK4 is perfectly suited to have flowing dusty plasmas. Do you have an idea for an experiment to get similar results in experiments on the ISS?
Yeah, I mean the two parameters that we're changing here with particle charge and the flow speed are both experimentally controllable parameters that you can change in experiments on the PK4. So you could have easily have an experiment, and PK4 was designed to study flowing complex plasma. So you could have an experiment where you use some sort of an obstacle that's maybe fixed in place, or like maybe instead of a spherical obstacle, you have like a disturbance to the electric field, and then you have a flow of complex plasmas through that to see how that changes the flow. So maybe not the exact same experiment, but a similar experiment where you disturb the flow in some way and see if you get vortices after that. So the PK4 would be perfect.
So this is more an experiment for the public flights. You have one.
Yeah, maybe just as a comment. So we did more or less like the experiment that you suggested. So we have a wire in a dusty plasma under microgravity conditions of a parabolic flight. And then we change the electrode bias potential, and so we can shift the dust clouds up and down. And so then we can see the streaming of the dusty plasma around such an obstacle. And we also see these bow shocks, and we are just analyzing the experiment. And so we are very happy to see your simulations. Thank you very much.
That's very interesting. Thank you.
Perfect. Thank you. So, thank you, Ishita, again. The next presentation is by Peter Hartmann from Wigner Institute in Budapest.
Yep.
And he's giving a presentation on...
Those. Okay, title should also come up. Yes.
Anisotropic interparticle interaction.
Yeah, so thank you very much,
Peter.
Robertus. Yeah, so the topic connects to the second topic of Shita, so this anisotropic chain formation and all these things. Well, I am always the stupidest here who has to talk. So this work was, of course, made in a collaboration with Wigner in Hungary, Baylor University, and Auburn in the US, with all the authors. So, yeah, so the motivation is that in the early days of PK4, when it was turned on and everyone was really happy, well, I was not there, but as I understood, one of the early observations was this chain formation, which is not completely surprising, but as I know, it was not that much anticipated as it was. So it was more dominant than it was expected, so to say. That's what I heard. So it is quite a robust feature, which happens under many conditions in the experiment. So, yeah, so the question naturally rises, okay, why do these particles align into chains? And yes, of course, we heard also that electroradiological effect, or even things that we know from radio frequency discharges, we have this wake field formation. So these are all effects which can lead to particle chain formation. But the tiny problem is that if one looks into the theory, so to say, phenomenological understanding of these phenomena, the effect of the anisotropy, I mean, clearly you need anisotropy to form chains, all depend on, so to say, the Mach number or some variation of the Mach number. So at the end, it depends on the drift velocity of the ions. But we are in a DC discharge in the positive column where you have something like 10 volts per centimeter electric field. So if you just assume some typical numbers for DC discharges, then you end up with ion drift velocities which are much smaller than the thermal speeds. So if you just plug these numbers somewhere in this phenomenological formula, you get something like a few percent of anisotropy. So the question is whether this is actually enough, or is there something else going on in addition to this? So to kind of get closer to the answer to the question of why do dust particles form chains, well, it was clear from the very beginning that we need a very multi-length scale and multi-time scale approach, because we have to resolve the fastest time scales of the electrons, then there is 100 times slower time scales of the ions, and then there is a 10,000 times smaller, longer time scale of the dust particles. So to cover all these orders of magnitude in space and time is, well, not a single person job. So that's why we kind of form this informal collaboration between the teams. Everyone is putting in expertise. We have access to the real PK4 data, of course, thanks to you. But at Baylor University, they built a kind of replica system of the PK4, which is as close as possible replica. And they have the dryad simulations developed, which is a kind of simulates the ions with the dust interaction. At Wigner in Hungary, we have some expertise in discharge modeling, and we also built a PK4, I wouldn't call it replica, it's kind of a PK4-like system, because it's more adapted to what we can do, what we can simulate. And at Auburn, they have theoretical expertise. For example, just 2 days ago, I got on archive the paper which describes anisotropic atypical, diffusion and transport in this anisotropic system. So, Yeah, so still the motivation part. In the experiment up there, 400 kilometers above our heads, of course, there are lots of diagnostics, but discharge diagnostics was not the main focus. So actually, there is a camera which looks at the discharge, the emission of the discharge, but it is a slow camera, something like 60 frames per second or something like this. On this time scale, the positive column looks completely nice. And also, if I run the simulations long enough, so I just set up a simulation, a cylindrical to the long tube, 40 centimeters, 3 centimeter diameter, so something which represents this system. Of course, if I let the system, the simulation run long enough and average the, let's say in this case, the electron excitation rate, so this should translate to the light emission, then of course I get the typical structure of the DC discharge, the negative glow, the dark field, and the positive column, and it's okay, so the dust should be somewhere here. But if I increase my time resolution, then I see that the same thing is the same simulation, just shorter time, looks completely different. And if I make a movie out of the time evolution, then we see that actually this nice, smooth something is actually composed of very quickly moving ionization waves, fronts. And if we just look at the electron ion density evolution and electric field evolution, then we see that there is a very strong modulation of these quantities. So now the question is, okay, then we have this environment instead of a stable environment, so how does that change the interaction? And yeah, so the two experiments that we have on ground is the PK4 BU, so Baylor University. So here a bonus, you have some of the authors here, Trul, me, and Jorge. And then we have the experiment in Budapest, which is a plain parallel, well more defined, no curves, no strange flanges, whatever, very well-defined conditions, but the same diameter, some lengths of 40 centimeters. And so we use these experiments to, first of all, verify if what we see in the simulation, so that was the order in time how this developed, so these ionization waves are really present in the experiment. To do so, we used the Baylor experiment because they had the fast camera. So from the simulation, this is time, this is space, so cathode, anode, time, and this is the emitted light, so to say, so the ionization excitation source, which is equivalent to the emitted light. And then we see the time and space evolution of these wave fronts. So we can see that there is a slower wave, a faster wave. It's quite complicated, but so this is the region where the camera can capture, which we use in the experiment. So just compare the experiment with the simulation, we see that it actually, it's a perfect match. So we have the slow part, the fast part, in the middle we have some bifurcation, everything is there, all the features which we see in the experiment and the simulation are the same. So that's quite promising. Okay, now we believe that the simulation is correct. So then, okay, then we can use it to target some questions, which includes, yeah, first of all, identifying the anisotropies, then look at anomalous diffusion for these systems, do simulations to get more insight into what happens in the discharge, then embody simulation, this will be the dryad to capture the dust dynamics and interaction with the ions, and then also look for experimental conditions where we don't have these waves, or let's see, map the conditions where we have and we don't have. So this is just a nice colorful plot to show what you can expect from a simulation, which is in some sense what more you can expect than from simple measurements. So these are all quantities which are fairly easy to extract from the simulations, so all the electric field components, all the densities. This is just one snapshot. Energy distributions, yeah, electron ion velocities, axial, radial, all these things we can extract. So in principle, what we can do is just put a dust particle in the middle somewhere here and look how its local environment evolves. And well, that's what we do. So we put the dust particle here. Well, we don't, in the simulation, there is no dust. We just measure the local plasma parameters at that point. So this is how this is represented. And if you look at some fundamental parameters, then we have the evolution of density, ion density, electron density, axial field, and ionization rate. So what we see is that first of all we have an overall oscillation, quasi-periodic. It's not completely periodic, but it has a typical frequency of something like a few times 10 kilohertz. We see a very strong modulation of the density. So let's say the minimum and maximum density ratio is 7:1. So this is quite a big modulation. Also the axial electric field, we saw field reversal. So typically it's negative. So it is driving the electrons to the positive direction. But then during the wave activity, we have periods of field reversal. And the total ionization rate, which is which you need to have to sustain the discharge, also comes in distinct peaks, where between the peaks you have actually zero ionization. So as the time evolution goes, so we can, here is just a zoom of the continuation of this curve. So you can see that first you have a development of a strong peak in the electric field. That will drive ionization, and due to ionization you will have a buildup of the charges, and then you have a much slower time scale where you have drift and ambipolar diffusion, which then kind of removes the charges. And okay, in the experiment we also have the feature which is called polarity switching, and we're also looking at, and also this power supply in the experiment is not very fast in polarity switching. Something like 200 microseconds is the switching time. It's something like a linear ramp in voltage. So we were looking at that condition where we have a linear ramp in voltage from minus, so to say, 800 volt to plus 800 volt. And what is the response of the discharge to this condition? And what we see in the discharge current from the simulation that, decreasing the magnitude of the voltage to zero, of course the discharge switches off, and it actually does switch off for a short period, for half of the switching time, so let's say 100 microseconds. But then it ignites again. I mean, some charges must still be left. The ignition is quite quick, and then it stabilizes. And the axial electric field shows also a nice feature. I mean, we have these oscillations before and after the switch. After the switch, actually, they appear to be larger, the first few peaks. But we have also some interesting feature which we see in here, some kind of pre-ignition or something. We don't really see this everywhere else, but strongest we see it in the radial electric field, or even better say, we were also looking at the radial, what is the radial forces acting on the dust particles, so what we could extract from time average, for the dust feels the time average, so to say, in the fields. So it is very nicely parabolic confinement potential up to over half a centimeter. So in the center, the radial confinement is really very parabolic if you have a single particle sitting there. And the strength of this parabolic confinement is what is shown here, and we have a very strong radial push to the center of the particles during the reignition, which is interesting. So anyway, now we have the time evolution of the local plasma parameters, where we should have the dust. So now let's put in dust in the simulation. So we use the dry simulation. It simulates ions and dust. So this is the equation of motion of ions, which includes all kinds of interaction between ions, between ion and dust, external fields. And this is where all these local plasma parameters come into these equations. Through the charge, I mean, the charge is also, of the dust is also calculated with OML for the ions, but counting the impacting OML for the electrons and counting the impacting ions. So here comes the discharge parameter, also the confinement, radial confinement. And we compare two cases. One, if we first average in time the plasma parameters, so this would correspond to the case where we have a smooth positive column, so no time evolution, no waves, and calculated the charge. You can see here, it just shows some fluctuation, statistical ones. Just putting a single particle in the center. And then the second case was where we included the time evolution of all these local plasma parameters. So then you see also an evolution of the charge. The overall charge is smaller, but it has a strong modulation. And then, of course, the dryad simulation gives you also potential distribution and ion density distribution. Already you can see from the potential distribution that this column is for the time evolution, so when we have the changing conditions. Actually, the anisotropy, although the charge is smaller, but the anisotropy seems to be larger. And to quantify this, here 4 fixed dust particles. So these are only the ions are moved here now in this case. 4 fixed charge particles. Again, the charge evolution is constant versus evolving conditions. And so this is an output from the dryad simulation. And then we did a kind of fit, empirical fit. So we have Kuliukova interaction and some asymmetric Gaussian added to it, which should emulate, which should fit to this, and we fitted this to the observed potential distribution. And what we could see, what we already saw by naked eye, the anisotropy parameter is actually the 2 parameters in the x and z directional Gaussian, the asymmetric. So this asymmetric parameter, anisotropy parameter, is larger for the case where we have a time evolution in the plasma parameters. It's at least for the inner grains, for the single grain, and when we have 4 grains for the inner grains, it is much larger. Well, the end, grains at the end don't really, well, I mean, it's clearly the particles in the middle who keeps the chain together. The end particles have similar anisotropies. So the next step is to also let the dust move. So now we have an equation of motion for the dust, which includes, again, dust ion, dust, electric fields, drag forces. What was that? I don't remember. So yeah, also some thermal fluctuations. So this is the next step in the dryad simulations. We start the system from a blob of particles and then let it evolve. And with and without this time evolution in the plasma parameters, and then we can see the formation of the chains. And this is from the, this is just 20 dust particles, but we can also start 1,200 dust particles under such conditions, and then we can form these kind of rings, this kind of structure. And then we can look at different parts or just one layer. So this is 2 layers, the 2 outer layers, the particles, one can see the chains. This is just a cross-section along the axis. Again, one can identify the chains formed in the system. And depending on whether we use, again, the constant discharge local parameters or time evolution, or we just use the quantities at the peaks or at the bottom, depending on the choice of the local discharge parameters, one can really produce very different correlation, different states with different correlation functions. And this is from the experiment that I don't remember which campaign, but this is from the PK4 experiments. And clearly this case, which includes the time evolution of the local pulsar parameters in the ionization waves, is much closer. Okay, the last topic we also started is to look at under what experimental conditions we have or we don't have ionization waves in the neon discharge. Neon discharge, DC discharges are very old topics. Already late 60s, colleagues produced this map, which says there is diffuse and striated, diffuse homogeneous, and all different regions of neon DC discharges, positive columns. Typical PK4 parameters, a few tens of pascals, 1-2 milliamps. This is typically in this range, which is not very well resolved and also shows this very narrow range. So actually, we try to set up experiments both in Baylor and Budapest to make a more accurate map of these things, and also, of course, conditions like purity of the gas and all these things may matter. So there is some work to do here. Okay, and the movie crashed, but that was the summary. Yeah, just use it.
Okay, should work now, yeah. Thank you for a nice talk, Peter. I have a question. So I would like to connect your talk to Ishita's talk a little bit. So what we showed in this recrystallization experiment and in Ishita's simulation is that, in fact, you don't need much of this attractive term to form strings. So in this, and you say your estimate shows it's just 3-4% if you just plug the numbers into the formula. I think the plots, the interaction potential which Ishita showed, there is also, it's also of the same order. So in this connection, two questions. So first of all, how important are then all these ionization waves in terms of attraction? Because previously we were puzzled. We were looking for increasing the Mach number or whatever. Is it now essential? And the second question is, of course, what is the resulting interaction potential in your case? Is it long-range attractive or long-range repulsive?
Mm-hmm. Okay, thanks for the question. Yes, I agree. You don't need a lot of anisotropy, and also agree that you don't need attraction. I mean, it's enough if you just have less repulsion in one direction. That is already enough. And yeah, I mean, ionization waves are, I think, not essential. I mean, you saw even when we used constant local plasma parameters, we still got chain formation. But ionization waves adds, so it makes it stronger. So as you could also saw the pair correlation function, everything, it was more ordered. There was more anisotropy in the potential if you had ionization waves. To this, and yes, also the potential doesn't need to be attractive. It can be just less repulsive in one direction. And this potential, which we showed, I mean, yeah, it had similar to what you also showed. It had the Yukawa repulsion. I mean, this negative. I mean, so this singularity, so to say, at the particle, and then it was just added a softer decay to the tails. But of course, the softness of the decay was different in x and z directions, and that's what introduced the anisotropy.
Okay, thank you.
Yeah, thank you. It's really very interesting to see that simulations and actual plasma match up so nicely. One thing I noticed is you have density fluctuations in the ion density by a factor of 4 to 5,
Yes.
with a frequency of around 20 kilohertz or so.
Yes.
Does that make a sound? I mean, it might just be out of hearing range, but density fluctuations of this magnitude, this is
Yes. Well,
translated to pressure that is significant.
Probably if you would sit inside the discharge tube, you probably yes. Well, I never thought about this.
Yeah.
I mean, certainly you don't hear anything from the outside. So it's a low pressure environment.
Yeah, it's 10 Pascal or so.
But yeah, that's an interesting approach. I could look at this. Yes.
Yeah.
So the entire discharge power is just half a watt.
Yeah, but half a watt of
actual
acoustic power, that is something you can very well use.
Yeah, but this is the entire power that you have.
And also you could tune your length of your discharge tube to have some resonance at that frequency. I mean, yeah, it's not a big deal just to connect the microphone to the tube to glue it on.
That's only the electron and ion density, which is only 10 to 4 or 10 to 5.
Yeah, so it's probably the overall density is just too low, yeah.
Yeah, but still it has pressure.
Yeah.
Peter, you had in the forces acting on the particles, there was a drag force.
Yes.
And there's also ion drag and neutral drag, I guess. And how important is this force for your for forming strings? And since the ion drag force, there are different formulas and different, there's some uncertainty, I think, in the ion drag force.
I mean, for the ion drag, you don't need a special you don't need a special term because you have the term for ion dust interactions, which takes care of it. Because when you have more ions hitting your particle from one side and the other, then there is momentum transfer. So the extra term is only for the neutral drag, which is simple Epstein formula, I guess. But yeah, I'm not familiar with the dry edge simulation in that detail, how these details are taken into account. But yeah, again, so this the electrons are treated as a Boltzmann distribution background. So electrons are not simulated; they are assumed to be thermal, which is, I mean, in general, not true for a high density whatever discharge, but positive column, so to say. Ions and dust is treated. So ions, interaction with dust and ions, you have repulsion, but you have also impact. So you have the charging is calculated from counting the impacting ions, and also the drag force is calculated from that.
Thank you.
So back to ionization waves, question which probably you are not able to answer, but what about the ionization waves in dusty plasmas? So together, so when your ionization balance is coupled to the dust.
Well, we always plan to do something. I mean, just model the presence of a dust cloud, an extended dust cloud with some extra loss term, some fixed, something, some kind of continuous region where you have extra losses. Whatever charge gets in has a probability of getting lost somewhere. And of course, you could also add some charge to this cloud. But we never did it, so I mean, definitely dynamics, this 20-something kilohertz is too fast. I mean, the dust particles feel only the average, but the question is of average of what? Because if you do the averaging before you do the calculation of interaction between ions and dust, or you calculate the interaction between ions and dust time resolved, and then average the effect in time. And this is the big difference. So what we say is that you get a more accurate description if you first calculate the interactions time resolved and then average the effect. So because it's not linear. I mean, it's a nonlinear response, so you cannot. It doesn't matter when you do the summation.
Okay, thank you.
Okay, so thank you, Peter. Very nice. Again, I want to mention that there will be an overview talk about PK4 in the next session. So Misha Pustilnik will give you more insights and more background, of course, on PK4 in the next session. André Melzer from the University of Greifswald, he's now talking about the next step for a project for the International Space Station, which is called Complex Plasma Facility. And this is a science definition team work we did with DLR and NASA, and also ESA was also involved. And they are already in the phase B study with industry, so that's quite interesting to see what's the next steps in plasma crystal and complex plasma research. Andre.
Okay, thank you very much, Hubertus. So, yeah, as already mentioned, I would like to speak about a possible successor experiment for PK4, and that's the compact experiment, the complex plasma facility. And it is intended as a multi-user facility that can be used by many participants, and this is also reflected in the wide variety of countries that are here in the compact SDT. So just let me start with some more general overview over dusty plasmas or complex plasmas. Dusty plasmas are generally a situation where you have particles of micrometer to nanometer size immersed in a gaseous plasma environment. And that has impact, of course, for astrophysical situations where you have dust particles in the planetary rings or in cometary tails or in interstellar clouds. It also has applications in technology where we use reactive gases to deposit films or to manufacture semiconductors or to etch semiconductors. But we are, of course, more interested in the fundamental situations of dusty plasmas. So we are interested in plasma-dust interactions or the dust-dust interactions where we can form strongly coupled systems. So let me just summarize some of the interesting properties of dusty plasmas. So as I already mentioned, we have particles of the order of micrometer immersed in a gaseous plasma. The particles, they attain high negative charges due to the inflow of plasma electrons and ions. So typically a dust charge of 1 micrometer size has about 1,000 elementary charges, so it's highly charged. But the charge to mass ratio, the Q over M, is extremely small due to the high mass of the dust particles, which means that all the dynamical timescales are very slow, so easily observable by cameras. Also, the interparticle distance is of the order of a few hundred micrometer, which is also very well suited to be observed by video cameras. And so all the temporal and spatial scales are perfectly suited for observation. In addition, we have low frictional damping of the system because we are operating in a gas at low pressures. So all the dynamics are not overdamped compared to colloidal systems. And as I already mentioned, we have strongly coupled systems where we can study fluid systems or even crystalline arrangements of dust particles. And we can have a nearly force-free environment, at least if we do these experiments under microgravity. So if we do these experiments under gravity conditions, so this is a side view of a plasma discharge with dust particles. So here's an upper electrode, here's the lower electrode, and under normal gravity conditions, the dust particles are forced by gravity into the plasma sheath, where we have strong electric fields that counterbalance gravity. And so there we have strong counteracting forces. So this is a stressed system, also in a non-equilibrium environment where we have streaming ions, electrons, and so on. But if we do these experiments under microgravity, then the dust particles can fill the entire plasma volume under nearly force-free conditions. And that's, of course, what we want to investigate and what has already been realized very early in the development of the field of dusty plasmas. So that then it was clear from the beginning that microgravity experiments on dusty plasmas are essential and are necessary to be performed. And our colleagues from Garching and the Russian colleagues, and also with the help of ESA and the Gießen colleagues, they have developed various types of experiments, the PKE Nefedov, PKE3+, PK4 experiment, which had been already on the ISS. And there have been a number of groups also performing parabolic flights in addition to the experiments on the ISS. And now, as already mentioned, we would like to have another experiment, the compact facility, as a successor of the PK4 experiment on the ISS. And the question is, of course, why we need another experiment, and what are the new features of compact that make compact interesting. And the answer is that there had been some new technical developments that make it possible to address new scientific questions, or maybe even put the other way around, so the drive for addressing new fields of interest, technical developments have been performed to be able to address these questions. And so these questions are listed here, and I will go to some of them in more detail in the following. So the possible topics that we can address with this compact experiments that have not been possible before could be statistical, or from the field of statistical physics, where we can have a look at the equation of state of the system, deviations from the ideal gas, transport properties, non-equilibrium thermodynamics of deviations or results from fluctuation theorems. And this is possible because we can observe a large number of particles and watch their positions, their velocities, their accelerations with very high accuracy. Next thing is that we would like to use active and non-spherical particles. So this is something that has not done before in too much extent. So that would open up quite new field. And there one also is interested in questions of structure and ordering of such a system. Then the statistical physics in comparison with the normal spherical particles, questions of turbulence, waves, and rheology, and collective effects using active particles or non-spherical particles. Then, of course, since we have systems with a large number of particles, we can study solid-liquid phase transitions because we have also strongly coupled systems. The particle interaction is so strong that we can enter the crystalline regime of the particle arrangement, so we can also try to study these solid-liquid phase transitions in very detail. We can try to form glass states and glass transitions or also supercooled fluids. Since we have only low frictional damping in our system, we can also start to investigate nonlinear dynamics such as turbulence or nonlinear waves. And as I already mentioned in the introduction, so of course also dust in more astrophysical situations are of high interest, so we can try to study some aspects of planetary physics in our setup. So something like dust charging under UV radiation, for example, dust mitigation, dust transport, and so on. And as a more general point, of course, if we have the dust particles and then understand their behavior, then we can also use these dust particles as probes for the plasma environment. Okay, so to be able to address all these questions, so we need extended particle systems at low gas pressure. Maybe we would like to have the ability to compress our system, into a solid state, for example. We would like to have versatile manipulation of plasma parameters. We would like to have a 3D observation of or 3D particle tracking to follow the particle dynamics in 3D. And of course, as novel experiments all do, so we want to make use of machine learning for data reduction or fast experiment control and experiment assessment. So that makes it necessary to produce our plasmas in a large chamber with variable electrode distance. For the manipulation of the plasma parameters, we would like to have segmented electrodes in the plasma chamber. And for the 3D observation, we would like to have a stereoscopic camera system. Yeah, and I would like to now address some of these more technical situations here. And so this is a sketch of how this experiment might look like from the phase B study of OHB. So with the central part here, the plasma chamber, and I will start with a description of the plasma chamber. As already mentioned, so this will be a quite large chamber, so the electrode diameter, the inner electrode is about 80 millimeters in diameter, the outer electrode is 120 millimeters in diameter. Electrode separation is a variable, as already mentioned, between 30 and 80 millimeters. The dust particles will be shot into the discharge by dispensers that have already been used for quite some time also in PK4 and so on. And so the new features are essentially the segmented electrodes and the variable inter-electrode distance. Another important feature is that we have a dedicated RF excitation of our plasma. So we have, since we have segmented electrodes, we have 2 electrodes on the upper side of the plasma chamber and 2 electrodes on the bottom side of our plasma chamber. So we have 4 independent electrodes. And we use a 4-channel RF generator to independently set the RF voltages and the RF phases on the 4 electrodes. That gives us a wide variability to change the plasma situation and the plasma parameters and the confinement for the dust particles. And what one is able to do with such an excitation technique is that we are able to produce very extended homogeneous dust clouds without any void. So that shows that we have a very nice force-free environment for the dust particle system, where we can then try to study all the questions that I have mentioned before. In addition, we would like to have a 3D diagnostic for the reconstruction of the 3D particle trajectories. So far we have employed that on parabolic flights. We use a 4-camera stereoscopic camera system that looks at a smaller field of view of the entire dust cloud and is able to reconstruct the 3D particle positions in this small field of view. But nevertheless, in this small field of view, we have still a few thousand particles that we can follow and track. So this is an overview of the entire camera systems that we would like to have for compact. So here in the middle we have the plasma chamber. Then we have 2D diagnostics that give us an overview of the entire dust cloud, a detailed camera that looks in 2D into a sub-fraction of the dust cloud. And on the other side, we would like to have the 3D stereoscopic system that will record the dust particle motion with 4 cameras in a smaller subfield of the dust cloud. And so from our parabolic flights, so we are able to reconstruct particle trajectories in this mentioned field of view. So these are particle trajectories, and color-coded is the velocity in the y direction of the particles. We can, from the trajectories, we can also calculate flow fields, for example. And as I already mentioned, we also would like to use machine learning techniques to make some control or assessment of the dust particle arrangement on the ISS. So the idea is that we have some kind of machine learning tool on the ISS that can give us a quick look onto our data and transfer, for example, the 3D positions of the particles in the field of view of the stereoscopic camera down to Earth, so that we can have a quick look assessment of the particle structure. And so one is able to decide whether to continue with the experiment, whether to start a new experiment, whether to add new dust particles, and so on and so on. And so the idea of reconstructing the 3D particle positions using a machine learning algorithm could look like this, that we have, with our 4 cameras, I've only shown here, with our 4 cameras, we somehow produce a voxel field where we transfer the intensities that we have measured in the different cameras into this volume field, so that we have the intensities along the line of sight of the different cameras. And we feed this volume field into a neural network that basically does some kind of feature extraction, some sharpening also, so that it makes from a blob of intensities is able to reconstruct a single position of a particle. And Yeah, so this we have also employed for our data from the parabolic flights. And so this is a comparison of our standard algorithm, the so-called shake-the-box algorithm, where we can calculate the 3D particle trajectories. And this is what we get from this artificial intelligence particle reconstruction algorithm. And you see this is quite similar. It's, of course, you see there are not so many particles reconstructed as for this more sophisticated algorithm. But if we tune this, for example, if we do this AIPR onto 4 subfields of our camera data, then we get a more reasonable agreement between the sophisticated algorithm and the machine learning algorithm. And the machine learning algorithm is much faster than the sophisticated algorithm. Okay, so here's an overview of the design of the compact experiment so far. As I already mentioned, so this is done in the phase B study together with OHB, and so this is the design at the moment. So in the center we have the plasma chamber. On this side we have the stereoscopic setup. On this side we have the 2D cameras, and below here we have all the vacuum and gas feedings, the camera drivers and so on. And here's the power distribution unit and video recording. In addition to the features that I already mentioned, we would like to have a plasma glow camera to get an impression of just what Peter just had told, to have an impression of how the plasma glow is behaving. Then in addition to the illumination lasers, we would like to have a manipulation laser which tries to push the particles, and so we have a means of manipulation of the particles. And other manipulation devices could be UV illumination. That would be interesting for the questions of particles under planetary conditions. We would like to have a spectrometer to have a more view onto the plasma glows and the associated atomic lines. We would like to have temperature control of the electrodes to manipulate the dust cloud, and an arbitrary function generator also to manipulate the dust cloud. And with that, we hope to be able to address the scientific questions that I had presented, and so thank you very much for your attention.
Thank you, Andre. Are there questions?
Hi, thanks for the nice introduction. I was always wondering when seeing your stereoscopic camera setup that actually the angle between the views is not that large. I mean, typically, when you say stereoscopy, you would put it in 90 degrees. I can imagine that it is technically difficult. It's much easier to fix it on a single plate and so on. But does that not reduce your resolution in Z, or how can you deal with that?
Of course, yeah. So the larger the angle between the various cameras, the more precise you can have the depth reconstruction. That's clear. So right now we are struggling of how to really increase the relative angle between the cameras, because they have to look from technical restriction all through one window on one side of the plasma chamber. But we hope to be able to get angles of about 20 degrees between the cameras, which would at least theoretically give us reasonable resolution in the depth. Yeah.
I was thinking about replacing the planar window of that window where the cameras look into something which has already some prisms or something built in, that actually you have some kind of reflective stuff as close as possible, practically inside the chamber, to increase these angles. But may not be feasible?
We haven't thought about this, I think. Yeah, so there are also more problems associated with the stereoscopic. So we have to also use some kind of Scheimpflug setup because to increase the field of depth and so on. So this is quite challenging to.
Yeah, well, then it's yeah, sure. Then it's static. Yeah, sure. Thanks.
Thank you. Marcus.
Maybe more for the general discussion, can you say something about the timeline of the project, the status, and what are the main obstacles apart from money?
Okay, so as I already mentioned, we are in phase B. So phase B will be until end of 2025, and then hopefully we go further into phase C and D. I think presently the timeline is that we should be able to start the experiment 2029. But then, of course, there's the question whether at that time we still have the ISS. But that are other questions that we have to address during the progress of the project.
Maybe a short comment on that. Of course, the agencies, DLR, I'm stuck. I'm stuck here. Huh? That's good. The agencies who are doing this project, DLR and NASA, they are, of course, know about the timescale and also the ending of the ISS. Maybe in 2030, maybe even earlier, because of problems with the hardware. This is seen as a project which might be already for a future space station or future free flyer, and NASA is always thinking about that and how to move this part to a new space station, for example. And to guarantee that, it's important to have the infrastructure the same, because all what is designed now is planned for a certain rack structure on the International Space Station with certain interfaces, cooling and venting and so on, and that must be identical. Otherwise, you're starting again with a design. So looking forward for that, open-minded, but of course, every change of the platform might also increase the funding necessary to realize the project. Do we have more comments or questions? Or in the program, there's a panel discussion announced. I don't know what do you want? So of course, panel for the future. We have the colleagues from PK4 who could give a short introduction of what are the future plans and for how long PK4 will be continued on the ISS. I don't know the ESA, what ESA wants to get with this panel discussion. Do we have someone from ESA? Yeah. I don't think we're sure either. Yeah, okay. Future possible funding? Right. Karin.
So Karin Kiewisz from the German Space Agency. One thing I would like to mention, so currently this is hardware built by DLR and NASA together, but if there's interest from other European countries to use this hardware, I think contact us and maybe we should talk about that, because it will have lots of capabilities and maybe we will find a way to make it also available to researchers from other countries.
Yeah, if you look into the list of researchers, there are ESA scientists involved since the beginning, and so it's not only Germany, it's European, it's American, and it's already multi-user facility.
Even more important that we start talking about people who are interested in it early, because of course funding is an issue, and if there's funding needed for people outside of Germany, I think we need preparations and a timeline.
We should definitely get more in contact to ESA. We lost a little bit the track since Astrid Orr left the field. There was Pepper. He was sitting here, but he disappeared. Who's now?
I'm supposed to take over. There's duties, notably on PK4.
Okay.
Because Giuseppe has moved to a different service at ESA. So normally I will be your point of contact.
Okay, it's good to have a point of contact, and we should discuss that. Okay, good. Markus, you want to say a little bit about?
Yeah, maybe a little bit about the future of PK4. I think we have an extension by ESA until 2026, and I think the apparatus is in a good shape. It was recertificated last year in October, and so we can continue. We have, as usual, 2 or 3 campaigns per year in 2025 and 2026. And then it depends on what will happen to the EPM rack. So will it be taken by some other experiment, and when? I think this is still open, and maybe there can be another extension as long as the apparatus is running. But otherwise, we will have to stop in 2027. And of course, we still have a lot of data which we have to analyze. So the research will definitely continue. And that's, I think, the future of PK4. And then we are looking forward to Compact, of course.
Yeah. So that would be the longest plasma crystal experiment on the ISS. So that's really good. And any more comments from agency side, from science side, or from the audience? Then?
So just yesterday, we heard that our irradiation experiment needs to go up 2027, early 27 at the latest. So we still get 6 months of time outside. So at least parts of ESA are apparently planning for a pretty short time left for doing like full-scale science operations.
From what I understand, there would be the orbiter that was going to be docked to the ISS around 2027, 2028, and from that point, I think it's going to get very difficult to support many astronauts on the ISS. So that's why I think also there will be a lot less operation and a lot less new experiments, a lot fewer new experiments that can be run, or things that need crew time. My understanding is that if there are automated experiments, maybe they can keep running, but things maybe like plasma crystal 4 it could be a bit more difficult to run them. regarding the exact time at which the station will be trashed, I personally, maybe the other people in the agency know better than I do, it's still not clear. Indeed, there's a window between 2020, late 2028 to 2030, but I don't think anybody's, has a precise date at the moment. I don't see any issue for PK4, at least until 2027. After that, it gets indeed it gets not super clear, and I think we need to be a bit more precise with that and communicate with the science teams a bit better with that. Yeah. But I guess as soon as we know more, we can relay the information to you.
I think this strongly depends on the problems, if they are increasing with the space station, small holes in the walls and things like that. So the oldest part is from 1997, 1998. So it's coming to 30 years after assembly, and that the stress on the ISS in space, in LEO, is very strong. Temperature gradients, vacuum, bombardment of micro meteorites or trash. So that a lot which might change the current schedule until 2030, I guess. So.
Yeah, I think the take-home message is sorry about that, and we will get back to you.
Okay. Okay, so then we are all happy. First of all, with PK4 and with the future laboratory, and we look forward for the next couple of years to do good science for plasma crystal research. Thank you very much, and enjoy the coffee. So we are nearly finished.